All right, so you must have received an email from me about the midterm exam. So I made an announcement, I made a post on OptiClass about the midterm exam, which topics are included, and how we're going to have it on the 3rd of May, exactly 1 week from now, in the morning on OptiClass. So you will not need to turn on your cameras. All you need to do is at 9:40 in the morning on Monday next week. You have to log in AutoClass, and in AutoClass there will be at the top. I'm going to put it at the top right on below the announcements. There will be activity named midterm exam. So you will have to click on it and attempt the midterm exam. There will be some numerical questions like, for example, sequence alignment filling in a sequence alignment dynamic programming table, and finding the scores. Those will be done. I will try to randomize some of those students as questions, and therefore each student is going to get a slightly different question, maybe numerically, but so you will be basically answering same types of questions. In statistical significance, for example, if the answer is a real number, I will indicate in the question whether you have to enter 4 digits after the decimal point or 3 digits. It will be indicated, specified in the question. Also, again, for hidden Markov models, there will be numerical questions about hidden Markov models. Again, when you enter your results, you will be, again, in the question will indicate how the answer should be written, and what precision, how many digits after the decimal point, in what format. So please read all of the question text to not miss any details about the format, because it will be some of the questions will be graded automatically, so that you have to adhere to the format strictly in order to get your grades. Oh, no, yeah, you're not going to, I will not have the WebEx meeting in the morning next week. You will not turn on your cameras. Or for questions, you will be able to send an email to me, okay? So I will check my emails in the morning regularly, and I will get back to you in at most 5 minutes if you ask a question, just like regular exam. I mean, if you raise a question and if you raise your hand and ask a question, and I will be able to get back to you in a couple of minutes. So yeah, please send me an email if you have some problems or about AutoClass, or if you have some questions or any issue about the midterm. You feel free to send me an email, and I will get back to you as soon as possible. All right. So the WebEx meeting will not be, I will not be in the WebEx meeting in the morning, but I will be in my office right here. I will be checking my emails, and I will be looking at the attempts, how many students are attempting it, or your responses, whether something, if there's something wrong with the questions, we can always adjust these after the exam too. I can regrade. I can, if I, for example, if I haven't miscomputed some result myself, and if you don't get your grade at the end of the exam correctly, we can always correct these later. Don't worry about it, okay? You will be able to see all the questions on one page, on a single page. All the questions will be presented to you on a single scrollable page. And as I said, there will be some short answer text questions as well. Any questions, and other questions about the exam? And the questions, their types will be, yeah, if you have any questions about the midterm exam, about particular questions, you can always send me an email as well. I will get back to you after the class today. And also the format is going to be similar to the example midterm exam. So here the sample midterm that we have. One question we have covered here. The questions will be similar to those short answer questions. Will be similar to short answer questions on the first page. As you can see, you don't need to write too many sentences to answer. For example, homologue, two sequences that are evolved from the same ancestor that are potentially evolved from the same ancestor sequence is a sufficient answer. What is a genome? You don't need to explain what a genome is in detail. It's basically the collection of all genes of an organism is its genome. So, or you may say the entire chromosome, the sequence of the collection of the entire DNA sequence on the chromosome. That answer will also be accepted. But what I want to show you is that at most one or two sentences. I think for each of them I had one sentence here as a solution. When there will be a question about sequence alignment like this, it may be a non-filled table that I may ask you to fill in with some scores, maybe, or partially filled, that I ask you what the scores are and fill the rest of the table. And the alignment, when I ask you the alignment, it will be like a short answer type question, in which maybe, or I will give some text boxes in which you enter one letter in every text box. I will have some number of text boxes, one after another, on top of each other, and you will enter your alignment results. If I ask you to enter an alignment, one letter in every text box, and again, if it's whether lowercase, whether it's case sensitive, I will indicate it in the question. So enter your sequences with all of the amino acid one letter IDs in uppercase or in lowercase. I will indicate that in the question. Yeah, so statistical significance and hidden Markov models, a question similar to that. You should expect a question again similar to this one. So this one is a really good representative of what the midterm is going to look like, what type of question. Instead of writing them by hand like this, you will be basically entering your questions in the text boxes, in the boxes that are provided on OT-class. All right, so if there are no questions about the midterm exam, I will continue with multiple sequence alignment, and hopefully we are going to finish multiple sequence alignment this week, which is also going to be included in the midterm exam. So we'll see, last time we started talking about multiple sequence alignment, and it's basically an alignment of more than two sequences. When it's two sequences, we call it pairwise alignment. By the way, I'm recording, yeah. And if it's more than two sequences, we call it multiple sequence alignment. And most of the time it's like at least 8, 10, sometimes 20. So this really gives the view of all these multiple sequences, how they are related to each other. If we look at this, we see that every pair of rows here, if you look at and choose 2, so if there are, or let's not, and the variable and, we usually use it to indicate the length of the sequence. Let's use the variable k. I mean, this is not something fixed, we can always change it later, but let's, if there are k number of there are k sequences that we want to align, you see there are k choose 2. All possible pairs of those k sequences are is one pairwise alignment. The first sequence and the third sequence, first sequence and the fourth sequence, first and second, fourth and eighth. So all these are pairwise, induced pairwise alignments from the multiple sequence alignment. And what we're going to do is, I mean, okay, given a multiple sequence alignment, it induces pairwise alignments, but the bad thing is that not every one of those pairwise alignments may be optimal alignments if you look at them. But the multiple sequence alignment itself may be optimal in the sense that looking at all the possible, I mean, looking at all the sequences simultaneously, you may see this is the best score that you can obtain. But if we try to align two pairs of sequences, we may make different choices to make the score between these two higher, which means that the pairwise it may not be optimal when it's shown in the multiple sequence alignment. But as I said, it means that this also shows that pairwise alignments, when we get an optimal alignment from a pairwise alignment, it does not always mean that it's biologically the most accurate alignment. Okay, because we are in pairwise alignment, we are trying to optimize a score, and we don't without any further biological information from other sequences, third, fourth, fifth, other sequences. The pairwise alignment, the only information it gets are these two sequences, and it tries to optimize to get the maximum score. But that maximum score, in the light of other information, the optimal alignment between a pair of sequences may not be the biologically correct true alignment. This is what I'm saying. Okay, so if we take a look at this alignment, we also mentioned that we can start from these pairwise alignments and try to build this multiple sequence alignment. And all the heuristics we're going to see do something like that. It's going to use pairwise alignments between sequences to build a multiple alignment. Because if we try to build this multiple sequence alignment from scratch using dynamic programming, so I'm going to talk about that here now. But there's also one note that I want to mention. And multiple sequence alignment algorithms are going to align anything that are given to them. Because I mean, it's just an algorithm. Even unrelated sequences could be aligned. But if it looks wrong, it means there are too many gaps everywhere, lots of mismatches, no columns that are conserved. It means that you're probably trying to align a set of sequences which are not related at all. So you should. This is a warning. Basically, before attempting a multiple sequence alignment of a set of sequences, you should first make sure that they are functionally related or there are homologs. So you need to first show certain amount of similarity before trying to align them. So yeah, why can't we use the dynamic programming solution, which always guarantees to give us an optimal alignment, and it will give us the optimal alignment in the case of multiple sequences as well. For example, if I have these three sequences, I could get the best score among these three sequences considering the multiple sequence alignment. By the way, the multiple sequence alignment score is usually indicated by a term called sum of pairs. So the sum of pairs score, sum of pairs. This basically, as the name suggests, we look at all pairs of scores in multiple sequence alignments. Since it induces pairwise alignments, we look at this pairwise alignment, compute the score based on some match, mismatch. Again, we have to be given as input in the multiple sequence alignment what is our match score, mismatch score, gap penalties, whether we'll be using BLOSSOM 62 for protein sequences or PAM matrix. So this should be given to us. So, but after we have the alignment, we can compute the score between the first and second sequence. We can compute the score between the second and third sequence, and we can also compute the score between the first and third sequence, okay? And these are basically pairs scores. If we sum up all those pairwise scores we have, we get the overall score of the multiple sequence alignment. And one way, instead of doing it like that, if we do this thing column by column, it will give us the exact same thing. For example, by looking at the first column, I see that there are 3 choose 2, which is 3 matches. First and second sequence is a match. First and third sequence is a match. Second and third sequence is a match. So whatever your match score is, if you multiply it by 3, you will get the column score of the first column. If you do it column by column, it will give you the exact same sum of pairs score, whether you do it in pairs of rows. All right. So usually we look at a column and compute its score by looking at all the possible cases. For example, here I have one match and two mismatches. CT mismatch, TC mismatch, and CC match. One match score minus two mismatch penalties will give the score for this one. So that's one way to measure, and this is called sum of pairs scoring. There's another measure like looking at the entropy at each column. And also, we also need to decide whether we have two gaps here. What do we do? Is gap a match? Or maybe we can just ignore those parts. It will be like two gap penalties. If you're looking at this column, we're just going to add two gap penalties for G gap. And I have another gap here. Gaps can be treated specially. It shouldn't be considered a match score of gaps. Maybe we can just ignore the penalty at that column. All right, so this is how we usually score them. But when we have three sequences, I already mentioned this earlier, that the dynamic programming solution is going to be computationally expensive. Its running time complexity will be exponential in k. So we will have a term that says 2 to the k, or we are going to see the exact complexity right now. But why we have exponential complexity, you are going to see, because combinatorically, the number of gaps, the types, where we can put them, we are going to have many different choices. Our choices of alignment is going to increase exponentially as we increase k. So if you look at this, if this is a given alignment, you can actually consider this as, for example, the XYZ coordinates. Each sequence can be a coordinate in some space. Okay, so X, Y, and Z coordinate. And as you can see, the alignment starting from 0, 0, 0, we get the first letters from the first and second sequence. Third sequence, we have a gap, so we are still at the first. We haven't still yet arrived at the first character in the third sequence. So this is 1, 1, 0. Then we stay at 1. We consume the second character from the second sequence, and the first character from the second sequence is going to be consumed. So this can be the alignment path can be considered as a trajectory on 3D space each time we're moving to one neighbor. Each of these XYZ coordinates, they may stay the same or they may increase by 1. Just like we're moving on a two-dimensional dynamic programming table, right? When we were in the dynamic programming case, what we were doing was when we had a cell like this. So when we're here, we can only come to this cell from these 3 locations. So this one also the same thing that is here. Our alignment paths from here, we can go to this place, or this place. Those are the 3 possible options. In 3 dimensions, we are going to have 7 different options. Consider this 1, 1, 0. Where can we go after 1, 1, 0? We can be at 2, 2, 1, 1, 2, 0, 1, 1, 1. So if you look at the possible options, you can go from 1, 1, 0. There will be exactly 7 of them, and that 7 actually is 2 to the k minus 1. So the reason that we have 3 choices from here is coming from actually 2 to the power 2, which is 4 minus 1. Gives how many choices you have here to follow on the next trajectory. So we can consider our dynamic programming table that we had earlier for pairwise sequences. It becomes a 3-dimensional matrix. Okay, we start from here, gap, and we you could not understand. Do you have maybe this way of looking at it may be complicated, but it's no different actually than what we had here. If we consider the sequences here, the sequences were like A, C, T, G, A, whatever they are. Okay, so what we are doing here is that instead of writing, we had a table like this, right? And we were filling in this table. And now these tables, if we index these table rows by some numbers like this: 1, 2, 3, 4, 5, 6. Okay, and starting at 0, 0, 1, 2, 3. This is just a way of looking at it as a matrix indices. So we start at 0, 0. We start our alignment here. So the next thing, when we align something, if we go this way, when we're filling in our dynamic programming table, where do we go? We go to cell 1, 1. Or in other words, if you try to trace back your alignment starting from here, which you start from, for example, 5, 8. You start at the 5, 8. If this is the uh, fifth row is the last one, and 8 column is the last one here. So you start with 5, 8. Where did you come to this 5, 8? If you do the trace back on this matrix, you'll see that you're also in 2D. You are, for example, this is 4, 7. And you go left, which means that you remain at 4, it becomes 4, 6. So you also have, your alignment is also a trajectory starting from 0, 0 and going to 5, 8. Okay, in 2 dimensions it was like this. Then we have in 3 dimensions, we are going to have a third sequence. Just imagine a third sequence will be here put into this table, which is, it will be like a cube, a rectangular prism. And in that case, we'll have another option to, I mean, we can put these gaps in different places. If we don't have any gaps, each of them will be increased by 1. Like in this case, from 1 to 1, if we don't have any gap, we go to 2, 3, 2. So it's just like going diagonal here. Actually, maybe the following slide is going to show better. Okay, so the idea is the same. So in this was 2D alignment matrix. This will be our 3D alignment matrix, and these will be our 3 options. So if in order to come to this cell, each one will indicate something. Look at this, IJK. In order to come to a certain IJK cell, we can come from I minus 1, J minus 1, K minus 1, which means that no gap in any of those sequences. If you don't have any gap, you will follow this diagonal. If you have a gap in 2 of the sequences, if it was the first and third sequence, you have a gap in them, you're coming from this cell. If you have a gap in only one of the first sequence, you're coming from here. So we will have 7 options here if you look at these. You just try to think about how you can get these I minus 1s. So it will give you these. These are your all 7 options. And if we write the dynamic programming solution to this, it will look like this. If the dynamic programming solution, we are going to take a look at the score, the best score of aligning the first I letters with first J letters and first K letters of these 3 sequences. The best way to align them is to look at where this IJK, which what can be the previous case of previous column of the alignment. These are the 7 possible cases of that you can have in the previous, just one column next to this final alignment where the IJK is aligned. Okay, so this delta here basically is our score matrix. Okay, which basically tells us that what is the match score of matching VI, WJ, and UK. So this is a lookup to the Blossom 62 table, or your match score or mismatch score. This time you just need to extend it to 3 things, and you can use that column score, the sum of pairs score that I mentioned, for just these 3 letters. Just what is the score of that single column where one of them is this character, the other is this character, and the third is this character? What happens if 2 of them is a gap? So these are just the right hand side is just a lookup table, and the left hand side is our regular 7 different choices we can have that can precede this. So this is the dynamic programming solution which solves optimally. It will find how to align 3 sequences with each other. But you see, it's still, and its complexity will be O(n) cube. Okay, if all of them, or if all 3 sequences are of length n, if all of them are of length n, I will have ON cube complexity here, because in order to fill in each cell, I need constant time. It's always 7. All right. So when you write it like this, O7n cube, because I have n cube such cells to fill in. To fill in each one of them, I have 7 options. I do this. I compare these 7 things with each other and find the maximum of them in constant time, which I spend this is constant time, so which is equal to O(n) cube. Okay, so it still seems polynomial. It's not exponential. It doesn't seem exponential in k, but actually, if you generalize it to k sequences, it will be something like this: O2 to the k, n to the k. As you can see, our time complexity will be exponential in k. For 3 sequences, it's still doable if you can spend O(n) cube time. But for more sequences, when k gets 20, so since it's exponential, it's going to increase rapidly as k increases. So practically, dynamic programming, this solution is not used in multiple sequence alignment algorithms because it's really costly. Okay, so yeah, this is in general, as k increases, this becomes the running time is going to be exponential, 2 to the k, n to the k, and the space that we need is also going to be n to the k. So this is the running time. The space complexity is we need a table of size n to the k, n to the power k. So space also is exponential as the number of sequences increases. So this discussion that we had basically states that dynamic programming solution, which solves the pairwise alignment problem, is not feasible, is not practical for multiple sequence alignment. This also shows that why multiple sequence alignment is a more difficult problem than pairwise alignment. Okay, it's extending our optimal solution is not feasible because the time that we're going to spend on aligning these sequences is going to increase dramatically. Now, therefore, do we just say this problem is unsolvable and not solve it? No. Even if this is like, I think it may be, there may be a proof that this may be an MP complete problem, I'm not sure. Which means that it's as difficult as many problems that are widely known, popular, like the traveling salesperson or Hamiltonian cycle or maximum clique type of problems. If it's shown to be in MP, the problem class MP complete or MP hard, whatever. I'm not sure whether it's MP complete. It's probably MP hard, as difficult as the problems here. But if you're given a solution, verifying the solution, I think it's not going to be in polynomial time. But anyway, so this discussion basically is about this problem, multiple sequence alignment problem, maybe a difficult problem, but do we just say, let's not solve this problem then? No. As in other difficult problems, what we do is we develop heuristics, or we develop approximation algorithms, which there is no guaranteed approximation algorithm for multiple sequence alignment as far as I know, but there are heuristics that we are going to see. A heuristic is basically a good idea that leads to a good solution better than random alignment. It never guarantees optimality, but it basically produces some solution that is acceptable. Okay, so this is what we're going to see as multiple sequence alignment solutions. We are going to see some heuristics. A greedy heuristic, we are going to start with a greedy algorithm, and then we are going to start with another algorithm. It may also be considered greedy, star alignment, and also a better, an improvement over star alignment will be the cluster omega algorithm that we are going to discuss. So these will be basically the algorithms that we're going to discuss. I'm not going to go into too much detail about cluster omega. I'm just going to indicate how it proceeds, and it will be similar to the other heuristics, progressive iterative alignments or yeah, progressive alignments that we use actually. All right, so it's going to start. The idea of all these alignments, the progressive alignments that we're going to see, they are the same. The idea is this: try to build your alignment. Let me get a new one. Starting from pairwise alignments. If you have a number of sequences that you want to multiply align, if these are our sequences, the first step we do is we already have an algorithm, dynamic programming algorithm, to pairwise align them. So let's pairwise align each pair and let's see what we get, okay? Then, for example, if imagine we do something like this. We pairwise align these two. After that, the alignment itself, you remember we have seen something called profile representation, right? We can convert this to a profile. The alignment result, whatever it is, could be represented as a position specific scoring matrix, or just each column of this pairwise alignment could be represented. In other words, after I align these two sequences, I can convert them into a probabilistic single sequence, which is going to be my profile. Now, after you have this profile, we also know how to align a sequence against the profile, right? What will happen if I align the third sequence to this profile? It will be now a profile of three sequences, and which will result in an alignment of three sequences. So this idea of adding a new sequence to the profile one by one is going to work. It's going to produce you a multiple alignment. But is it going to be a good one? How can we, the big questions we are going to have here, our degree of freedom here is that, do you really randomly start with two pairs of sequences and build a profile out of that and try to align them to the other? So here, the sequence order, the progressive alignment, the order of this progression is extremely important to the final multiple sequence alignment that you're going to get. Imagine you start your pairwise sequence alignment with two sequences which are most dissimilar, which has least sequence identity between them among the k sequences you have here. So you have k sequences. Which sequences are you going to start building this profile? Okay, then these two, maybe we also know how to do profile alignment. If we have two probabilistic sequences, we have also seen how to align them to each other at the beginning of the slide set when we describe how we can represent multiple sequences as profiles. So obviously, these algorithms, they're going to differ on how they make this progression from k sequences, each one of individual, which pairwise alignments we use, in what order to have this multiple sequence alignment, is how these algorithms differ from each other. I will show you three different algorithms. The first one is the greedy algorithm, which does this. Obviously, if we're bound to make more errors if we start with most dissimilar sequences, why don't we do the reverse thing then? I mean, start, if you want to make least amount of errors in your multiple sequence alignment building, start with the pairs of sequences which have the best similarity among them. Okay, and how do you determine which two sequences are most closer to each other? We have the pairwise alignment tool at our hand, right? So I'm going to perform k choose two alignments here. I'm going to align each one of these sequences with every other one. So 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5, 2 versus 3. So if I have 5 sequences here, I will have 5 choose 2 alignments, which is 5 times 4 divided by 2, which is 10. Okay, so I will first conduct 10 pairwise alignments. Before I build this one, I will have 10 pairwise alignments. And of each one of these alignments, they will result in some score, right? The score of alignment between 1 and 3, the score of alignment between 1 and 2, the score of alignment. So I will have 10 such pairwise alignment scores between all of them, and I pick the maximum one. For example, if 2 and 3 attain the maximum pairwise alignment score between them, what do? I align 2 and 3 with each other. After the alignment of 2 and 3 with each other, after I align 2 and 3, I get some alignment like this. Actually, I have this on my slides. So let me start with this iterative one. Where is that? The greedy. Yeah. So this, yeah, look at this one. So this is the algorithm actually. The greedy approach is describing the exact same algorithm that I'm talking about right now. For example, in this example, the first sequence and the third sequence happens to be most similar to each other. And after I align them, I get something like this. Look at this. Let me get this one. Look at this part. What does it look like? It doesn't look like a single sequence. It's actually profile. After this alignment, it's basically saying that A and A is aligned, C and C is aligned. So the first position is pure A. The second position is pure C. And the third position, I have a G and T mismatch. So the third position is a hybrid nucleotide, half G, half T. Then I have TAC, half G, half T. I may also have gaps at some places. So this basically, U1 becomes the profile. After you do the alignment, you get yourself two sequences that are aligned, and you can build a profile of these two sequences, and U1 becomes a hybrid profile sequence. So what you do, you remove original U1 and U3 from your set, you replace them with this hybrid new sequence U1. Now you have K-1 sequences in your set, right? You remove two of them, you introduce a single hybrid profile, but it's still a single sequence from our perspective. Now I have K-1 sequences to align. So I can repeat the same procedure in this K-1 case. I can try to figure out which one of these K-1, which pairs which pair in this K-1 sequences is most similar to each other. So I do another, this time K-1 choose two alignments. Maybe I can reuse some previous alignments, right? Do I really need to do K-1 choose two pairwise alignments here? No, right? For example, the alignment between U2 and UK, for example, or U2 and U3, I already did that in the previous step. So the only new similarity scores that are going to be introduced in this set is going to be U1, the new U1 versus the remaining cases. So which is K. There are K of those sequences. So I'm going to conduct another K pairwise alignments to see whether U1 is most closer to U2 or U2 is closer to UK. Again, at this step, my goal is to find the closest pair of sequences, and one of these pairs may be this hybrid sequence. Now if you don't distinguish between hybrid sequences and actual input sequences, these are also like hybrid sequences with 100% of the same amino acid at each column. Okay, so if you don't, there's no distinction basically, whether it doesn't matter whether it's a profile or an exact sequence. Because at the beginning of the slide set, as I said, we have seen how we can align two profiles or a sequence against a profile. So therefore, we can do that. So the algorithm basically is pick the most similar pair at each step, align them, generate a profile out of that alignment. So and progressively, this K-1 is going to become K-2, K-3, and at the end, you're going to have a single multiple sequence alignment of these K sequences. So here's an example of this algorithm on 4 sequences, S1, S2, S3, S4. What we do is we first conduct this 6 alignments. Depending on, I don't know what match mismatch score is, but the scores are just given to us here. So S2 and S4 seems to get the best score. So we use this alignment. Basically, after we have this score, it means that this score is an outcome of some alignment. We don't need to realign them. The alignment is also can be stored somewhere. And we see that this is the alignment. Now, S2 and S4 are removed from our set, replaced by something GTC T, or 50% T, 50% A, G, 50% A, 50% C. So we are going to replace this with a profile, and this profile, as you can see, it also shows an alignment by itself. The profile representation shows an alignment, and also since it's a profile, it can be then aligned with S3 and S1 to see whether S1 is similar to this profile or S3 is similar to this profile, or the similarity between S1 and S3 may still be larger than that. All right, so we can, at the next step, after this step, whether we are going to proceed with the alignment between S1, S3, or S1 and S2, or this profile, we don't know that. So we have to again look at the second step. We find the most similar pair of sequences and progressively build it like this. So this doesn't show the remaining steps, but we can just do it by hand. It's a really short sequence. Okay, so this is the greedy approach, the first algorithm that I'm going to show you. And it basically again uses pairwise alignments to build a multiple sequence alignment. So let's see whether we have any missing things here. Yeah, so we also talked about how we represent these profile at the beginning of the slides, right? So there are a couple of options that we can use these pairwise alignments to build these multiple sequence alignment. Now let's see. So we started from here. Okay, first of all, the multiple sequence, given the multiple sequence alignment, the pairwise alignments are induced from this. But is this the optimal alignment between X and Y? And not necessarily. This is what I was saying. So if we have three arbitrary alignments like this, can we construct a multiple alignment that induce them? Can we combine them into a multiple sequence alignment? We're going to see, not always possible. There are some conflicting cases where pairwise alignments cannot be combined into a consistent, which means that in an order that is sequence order specific, which also maintains the sequence order in individual sequences. So all these heuristics we are going to see, as I said, are going to be using these pairwise. It's going to start from these pairwise sequences, and sometimes pairwise alignments may not be consistent. We had an example about that. This one, if you remember, just think about if you look at these three sequences: AAA, TTT, TTT, GGG, and this GGG, AAA. So it's really an extreme case where we have these pairwise alignments. Look at these three pairwise alignments. How are you going to, is it possible to combine? Try to do it by hand. In order to understand this figure, just get these three alignments at the edges, write them on some paper, and try to put these three of them on top of each other to construct and since this is an alignment, you're not allowed to obviously move them left and right like this, because you will be disrupting the alignment. You're going to be destroying this pairwise alignment. Without moving them left and right, without changing the alignments, can you put these three on top of each other? Let's see. These two could be put on top of each other easily. I can put these GGGs, which is this sequence actually, it's right here. I can put this AAA TTT right above here, right? So TTTs are going to be on top of these TTTs. So an AAA is going to stick out like this. I'm going to introduce new gaps. But if you try to do the same thing with this, it will not be possible, because here the AAAs that are sticking out here for this sequence, because these T's, in order to align these two T's, let me write it here again. Let me try to annotate. with the pencil. So what I'm saying is that let's put these T's. I have four T's which are aligned like this. So the fourth one is above here. So it's like this T. Let me also change the color to something darker. So T, 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 and there's A, right? So the alignment, if I add these over this one, it's going to look like this. So this is the three alignments that are combined. If you combine these three alignments, it's going to look like this. Now, look at this one. It basically says that these two A's are aligned, but the way you put the the way this alignment between this one, if you add it to here, you see that A's are separated. There's no way to add this third alignment over to this one uh, because these two already used to combine into a three sequence, and here the pairwise sequence alignment you have between these two sequences are not represented. There is a pairwise alignment of these sequences again induced by this three sequences, which is different than what we have here. So which of these two edges you choose doesn't matter. You're always going to get some conflict at the end. The only way to not get any conflict is to ignore some of those pairwise alignments. For example, by combining our multiple sequence alignment by using these two edges, we actually use the alignment uh, to only this sequence. So we have, by using these two edges, we use the alignment of second and third sequence to the first sequence. In other words, if the first sequence is like a pivot, is like a reference point, you can use that to combine the pairwise alignments into a single alignment. It is possible, but when we were doing that, we ignored this pairwise alignment. So the next algorithm that we're going to see exactly does that, and it will ask the question. Again, we will have some degree of freedom. If we are given k sequences, which one of them to use as the pivot, as the reference? For example, is using TTDGG as the pivot the best way to proceed? Is it going to give me a good score? Or if I use this one, would I obtain a better score if I use this sequence as the reference sequence? That's the star alignment algorithm that we're going to see next. Okay, so uh, using pairwise alignments, it's not always. So we have to have some strategies to build consistent alignments out of these pairwise alignments. And one way to do that is we will have to ignore some of those k choose 2 multiple sequence alignments. We are going to have ourselves an order, a progression order, which is going to ensure that some of those pairwise alignments are ignored, but the good ones are used and put together into a multiple sequence alignment. So this was these slides that are in the middle here are actually very similar to what we had at the beginning of this set of slides, the profile. You see this profile representation, it's very similar. So it's a revisit of that profile representation because we are going to be representing in certain intermediate stages of our progressive alignment building, we will have to represent multiple sequences together as a single sequence, either as a profile like this. Look at this multiple sequences, 5 of them. I can represent this as a single sequence by saying in the first column I have 60% C, 20% T, 20% gap. So this is, we already know a way to represent this multiple sequence alignment as a profile. There is another way to actually represent this entire alignment as a single sequence, which is the consensus sequence. For example, I can say that the consensus sequence of these 5 sequences is the CAG, CTA, TCA, CGG. Why? At each column, I pick the majority of nucleotide that is occurring there. Okay, if there is such a majority. If not, for example, if there are ties, we don't have that in this case, but we could have ties there. We just break ties randomly. For example, what would happen if these two G's here uh, were two T's? So if I have two A's, two T's, and one G in the consensus string, am I going to write A here or T here? So I will have ties basically, which I will have to break if you want to decide on a single string as your uh, profile. Okay. So we usually do not use this consensus string approach when if we are going to use that greedy alignment. Instead, we can actually maintain all the information. So consensus approach actually removes certain information. It loses certain information when it just chooses the majority nucleotide at every column. For example, if we just choose to use T at this single as a single letter in this column, the fact that 40% of this column is C is lost if we just use the consensus string. Therefore, using this frequency-based representation or position-specific scoring matrices is a better way to represent the profile. So we can, we can align sequence against the profile, a profile against the profile using dynamic programming. Now, given two alignments like this, can we align them with each other? Yeah, we represent this as a profile. The second one also is a profile. Then we use pairwise alignment but what I'm saying is that combining these two alignments into a single alignment is nothing but pairwise sequence alignment by dynamic programming. Okay, but you can use the pairwise dynamic programming technique that we have seen to align this one against this one. If you represent this one as a PSSM or a profile, and you also represent this one as a PSSM or profile, we can align these two, can be aligned with each other to obtain another combined profile. And this is, so yeah, we can align these. We have already seen the greedy approach. Before starting the star alignment, I will now have, I think it's time for a break. It's 10:30 right now. So you may go over the greedy approach if you didn't understand it in the break. If you may want to go over it again if you didn't understand it completely. And after that, we're going to continue with star alignment, in which, as I said, one of the sequences in our set is going to be picked as a pivot, as a reference sequence, and we will be using the pairwise alignments to that sequence, to that pivot sequence, and it will be very faster than this greedy algorithm. After we have chosen the pivot, we just build the alignment by just writing those pairwise alignments to that pivot sequence one after it, on top of each other. It will give us the multiple sequence alignment. I will show you an example about this after the break. All right, so let me stop recording now.